In this video, we are going to be going over the remainder of section 3.2 over power functions and polynomial functions. So, first we have a definition. So the definition of a polynomial function of degree n is just going to be a function whose rule is a polynomial whose highest degree is n. And so that might seem a little vague. So a better way to express this definition would be to write the formula for like a general polynomial function of degree n. It's going to look something like f of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus dot 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 plus a sub 1 times x to the 1 and then plus a sub 0. So that is what a polynomial function of degree n would look like. Of course, here we would be assuming that a sub n is not 0. So I should put that. And of course, here n is just going to be some positive integer that is greater than 1. And the coefficients a sub n are just going to be constant real numbers. All right, so some examples of some polynomial functions would be like f of x equals 3x minus 2. This is a polynomial function of degree 1, in other words, a linear function. Or g of x equals x to the 4 plus 5x cubed minus 6x squared plus x minus 3. This is a polynomial function of degree 4. We could have a power function. So we have an example of a power function here. H of x equals 3 times x to the 5 is going to be a power function of degree 5. For the power functions, unlike the polynomial functions, so for the power functions, they are going to look in general like so let me put here power function is going to look something like f of x equals k times x to the a, where k and a are just going to be some constant real numbers. So unlike with the polynomial functions, where we require the exponents on the variable x to be like integers, with the power functions, we only have one term for one thing, and for the other, we do allow the exponent to be kind of, any real number. It doesn't have to be like a positive integer per se. Okay, and so when it comes to the graphs of polynomial functions, there's kind of some general things that we can say based on whether the degree of the polynomial function is odd or even. Also, another important ingredient here is whether or not the leading coefficient, so the coefficient in front of the term, or rather the number in front of the term of highest degree, whether it is positive or negative. So if we have an odd degree polynomial function with a leading coefficient greater than 0, then the behavior at the ends, well, we have some examples here of some graphs in blue, brown, and red of some odd degree polynomial functions that have a positive leading coefficient. And by the way, just for the record, the function in blue, this is just going to be f of x equals x. So just the identity function, which is like, of course, a linear function, but more importantly, it is kind of like the easiest example to understand of an odd degree polynomial function with a leading coefficient greater than 0. And so when it comes to describing the behavior at the ends, what we're talking about is what happens to the values of f of x if we let x go to plus infinity, as well as what happens to the values of f of x as x goes to minus infinity. And so we can see from all three of these graphs here, as x goes to plus infinity, the values of our polynomial functions f of x are also going to infinity. So as x goes to infinity, f of x goes to infinity. Then we're also interested in what happens as x goes to minus infinity. And as we can see from all three of the graphs here, as we let x tend to minus infinity, well, the values of our odd degree polynomial functions with positive leading coefficients, their values f of x tend to minus infinity as well. So the behavior at the ends for an odd degree polynomial function with a leading coefficient greater than 0 So we are going to have f of x goes to infinity as x goes to infinity. And f of x goes to minus infinity as x goes to minus infinity. And again, so we are talking about what eventually happens here. Like if we look at the graphs in brown and in red, well, if we look near the origin, it's not like we can say anything general about where the function's values are going. But it's as we get further and further away from the origin that we can determine that, okay, their end behavior is going to be, well, the function's values as x goes to minus infinity are that f of x is going to go to minus infinity as well. And then when it comes to the number of zeros for an odd degree polynomial function, just in general, regardless of whether the leading coefficient is positive or negative, well, what we can say is that there is going to be at most n zeros. Where n is just going to be some odd number corresponding to the degree. For instance, in the case of our simple degree 1 polynomial, rather our linear functions, so if we think about any sort of linear function with positive or negative slope, so that is, non-zero and well-defined slope, they all have exactly one x-intercept. And that is going to correspond to those polynomial functions having exactly 1, 0. And so that's going to be all the degree 1 polynomial functions. Okay, and then for the behavior at the turning points, so What we can say about an odd degree polynomial function is that it is always going to have an even number of turning points. That's going to be where the function changes behavior. So if we look, for instance, at the graph in brown here, it has 1, 2 turning points because it goes from increasing to decreasing and then back to increasing. So behavior of the number of turning points as well. There will always be an even number. And of course, we can see from the graph in red and the graph in blue, well, neither of those graphs have a turning point on it. Both these functions are always increasing. And so what this means is that they have 0 turning points because they never change behavior, but 0 is an even number. So there's nothing for us to worry about there. And what changes if we make the leading coefficient negative? Well, what is going to change is going to be the end behavior. So instead of having f of x go to positive infinity as x goes to positive infinity, we are now going to have f of x goes to minus infinity as f of x goes to minus infinity. So we could say the behavior flips. Which means f of x goes to minus infinity as x goes to infinity, and f of x goes to infinity as x goes to minus infinity. And of course, we could see that by instead considering the graph of f of x equals minus x. Which we can sketch a graph of here in pink. So again, if the value of the leading coefficient changes from positive to negative, the end behavior is just going to flip. All right, and so next let's talk about graphing even degree polynomials with a positive leading coefficient. So once again, we have 3 different graphs. This time they're all of even degree polynomial functions with even coefficients. I will point out that the graph in blue this time is going to be kind of like our easiest case to consider in this particular context. It is going to be the graph of f of x equals x squared. It's the graph here in blue. And so as we can see from its graph, as x goes to plus or minus infinity, f of x is going to tend to infinity. The values are just going to go up and up. So f of x goes to infinity as x goes to plus or minus infinity. And then when it comes to the behavior of the number of zeros, well, again, it's going to be that we have at most n zeros, except, this time n's going to be an odd number or an even number. Let me write above that n was odd. So behavior of the number of zeros, well, once again, it's that there will be at most n zeros, except this time n is even. So it's not necessarily the case with either even degree or odd degree polynomial functions that they'll have like an even number of zeros or an odd number of zeros. And really what it comes down to is just there being like repeat zeros or zeros of multiplicity greater than 1. But what we can say about the number of turning points is that there will be a odd number of turning points. So always an odd number of turning points. So if we look at all three of our graphs here, both the graphs in blue and in brown have exactly one turning point. They go from decreasing to increasing. And the graph in red, which again is another even degree polynomial function, it has 1, 2, 3 turning points. So again, an odd number. And once again, we're asked what changes if we make the leading coefficients negative. Well, again, the n behavior is going to flip. So we are going to have f of x goes to minus infinity as x goes to plus or minus infinity. Let me change this to pink too. Oh. And so to see that, we could consider kind of the most basic even degree polynomial function with a negative leading coefficient, which would be f of x equals minus x squared now. So it's just going to be the reflection of the graph in blue about the x-axis. Try to make it somewhat accurate here by plotting some points. So this would be a sketch of f of x plus minus x squared. And we can use that to understand the end behavior for all even degree polynomial functions with a positive leading coefficient. All right, so let's get into the examples. Okay, and in this first set of examples, we are asked to state whether each graph could be the graph of a polynomial function. If it is, state whether it could be a polynomial function of degree 3, 4, or 5. So basically, when we're looking to check if the graph could be the graph of a polynomial function, well, we just want to see some graph whose domain is going to be all real numbers. And then we want to make sure that it's just kind of, continuous with no sharp like turning points, like those that we might see with like an absolute value function or something like that. So in our first example, I here, we have our graph in blue. And yes, it's going to be a polynomial function. So we have this nice continuous function here whose domain is going to be all real numbers. And it has a finite number of turning points. That's another thing we could check because there are, the trigonometric functions, which can, if you squint the right way, resemble a polynomial function. But of course, those guys are going to have an infinite number of turning points. So requiring that there's only finitely many kind of resolves that discrepancy, if you will. All right, so let's look. So now we want to determine its degree. So this polynomial function has 1, 2, 3 turning points, which tells us that the degree should be even. And we could also kind of confirm that by looking at the end behavior. So when it comes to the even degree polynomial functions, their end behavior is going to be the same in both directions. So as x goes to positive or minus infinity, f of x is either going to go to infinity or f of x is going to go to minus infinity. And here, so as x goes to plus or minus infinity, we can see from the graph that f of x is going to go to infinity. So that also tells us that this is an even degree polynomial function. And so, yeah. We'll say yes. It is a polynomial function of degree 4. All right, I'm looking at our second example here now. So looking at the graph for example 2, well, we can see that the end behavior is opposites at the end. So as x goes to minus infinity, f of x is going to minus infinity. And as x goes to plus infinity, f of x is going to plus infinity too. And so this tells us that this is going to be an odd degree polynomial function. And if we look at the number of turning points, here's 1, 2, so an even number, which further confirms to us that this is an odd degree polynomial function. And it has 1, 2, 3 zeros. So we could say yes, it is a polynomial function of degree 3 or possibly 5, because even though we can only see 1, 2, 3 zeros here, that doesn't necessarily mean that the degree is 3. So we could just have a 0, or rather 2 zeros maybe even, of a multiplicity greater than 1. All right, and then for our last of these examples, so looking again at our graph, this time for example 3, once again we can notice that the graphed function has opposite behavior at the ends, so its end behavior is opposite. depending on if x goes to minus infinity or x goes to plus infinity. So that should tell us that it's going to be an odd degree polynomial function. And let's look at the zeros here. So there's 1, 2, 3, 4, 5 zeros. And so this can only be a polynomial function of degree 5. Like if we're only considering degree 3, 4, or 5 polynomial functions, then this can't be a degree 3 polynomial function because it has 5 zeros. And a degree 3 polynomial function has at most 3 zeros. Another thing we can check for is the number of turning points. So there's 1, 2, 3, 4 turning points, so an even number. So we'll say yes, it is a polynomial function of degree 5. All right, in the next example, we are going to use the following information about a polynomial to determine the function. So, or rather to determine a formula for the function. So we are told that it has a y-intercept 0, 9, and it has x-intercepts at -3, 0 and at 3, 0. And it is going to be a degree 2 polynomial function. And we are told that the end behavior is that as x goes to plus or minus infinity, f of x is going to go to minus infinity. So that tells us that the leading coefficient is going to be negative. So we could write f of x equals, and then since the x-intercepts are -3, 0 and 3, 0, and since it's degree 2, well, it's going to be a quadratic, and since it has these x-intercepts, that means that, well, for the x-intercept -3, 0, we are going to have a binomial factor of x plus 3. That way, when x is -3, we're going to have 0 for this binomial factor, which is going to multiply the other binomial factor and give us 0 for the product, which is why we have that x-intercept there. And similarly, for the other binomial factor, it's going to be x minus 3. That way, when x is 3, this binomial factor is going to be 0, and so we're going to have 0 for the product, and so that's going to correspond to our other x-intercept. And then, since the end behavior is that as x goes to plus or minus infinity, f of x tends to minus infinity, this means the leading coefficient's negative. So we can write negative a here. And then we need to check and see what the value of a should be. So since we're told the y-intercept, we can use that y-intercept to try to recover the value for a, but it's going to turn out here that a is just equal to 1. So, and we can see that if we just multiply out our two binomial factors. So we're going to have f of x equals minus a, and then we'll have x squared, and then we'll have plus 3x minus 3x, so those guys will cancel out, and then we will just have minus 9. So we end up with the difference of squares for the product because, well, the factorization was a difference of squares factorization. And so when x is 0, well, we are going to have 0 squared, which is just going to be 0. So we are going to have 0 minus 9, or just minus 9 in the parentheses here. and then times minus a. So we're going to have minus times a minus, so that's going to be a positive 9 times a. And we need this value to be equal to 9, so a should be 1. So we could say, kind of like when we were dealing with the quadratics earlier in section 3.2, we could write, okay, since f of 0 is equal to 9, this tells us that 9 is equal to minus a times 0 squared minus 9. So 9 equals minus a times minus 9. So 9 equals 9a. And so 1 is equal to a. And so f of x is equal to minus x plus 3 times x minus 3. Or if you prefer the unfactored version, minus x squared plus 9. All right, in our next example, we are told a cube has an edge of 3 feet. The edge is increasing at the rate of 2 feet per minute, and it wants us to express the volume of the cube as a function of m, the number of minutes elapsed. So we know the volume of a cube is just going to equal, so v is going to equal s cubed, where s is just going to be like the length of an edge. So we could use e here instead of s, but I don't know, I prefer to use s for side instead of e for edge. So this is just the general formula for the volume of a cube. Okay, and then we want to think, okay, so we can express the value of s as a function of m. So we're told that s of m from the information in the problem here is going to be equal to 3 feet, the initial length of the edge, plus 2 times m, because it's increasing at 2 feet per minute. So after 1 minute, the length of the edge will have increased by 2 whole feet. And so for the volume, we can say, okay, v of m is going to equal, well, s of m cubed which is equal to 3 plus 2m cubed. And if we wanted to expand this out, we would have, let's see here. So we would have 2m cubed, which is going to be 8m cubed. And then we would have, let's see, 2 times 2 is going to be 4, times 3 is going to be 12, and then times 3 again is going to be 36, so plus 36m squared. And then for our next term, we're going to have 3 squared is 9, and then times 3 again is 27, and then times 2 is 54, so plus 54m. And then finally plus 3 cubed, which is going to be 27. Let me double check that. So 3 cubed, 27 times 2 is going to be 54, and then we're going to have 4 times 9, 36. Yes. So this is the volume of the cube expressed as the polynomial function in the variable m, where m is just the number of minutes elapsed.